Hello problem solvers. Today we will solve an algebra problem. I saw this problem from another math channel called Your Decisions. That's the name of the YouTube channel. I want to discuss this because the author Press Walker discussed it in a quite high level way. I want to provide a more, let's say, a competition style, a style that is more aligned with the high school level. So please give this problem a try before watching on. So the first impression of this problem is that somehow you need to express higher powers in terms of lower powers. Of course, if we can actually find out the values of x, y, z, then we can just plug it in. But I doubt usually in a competition, in this competition problem, usually the answer is quite ugly. So try not to directly solve for the values of x, y, z. We will need to somehow express this in terms of these. So basically an algebra problem where you just manipulate symbols. But so the purpose of my channel, I would like to discuss some more, help you to be a better problem solver at the competition level. So I will try to introduce some facts that will help you. So here are some facts that if you are competing at the Olympiad level, you should know. So first of all, we have something called symmetric polynomials. So let me give you some example. So let's say I have 3 variables, right? Then let's say I have this. You can see that if I rearrange A and B, so if I substitute B in place of A, if I substitute A in place of B, the whole expression doesn't change. These would be called symmetric polynomials. And also we have elementary symmetric polynomials. They are the, let's say, the more elementary one. So let's say A plus B plus C. If you have 3 variables, the elementary ones would be these 3. As you can see, if you replace A with B, B with A, the expression doesn't change. So these are symmetric polynomial, but they are also elementary. Well, there is a definition. You can go to Wikipedia to look it up. But so I think you get the idea. So if you have four variables, you just A, B, C, D, and then you have 3 more terms, and then you can have ABC plus ACD plus BCD plus ABD. So those 4 would be the elementary symmetric polynomials with 4 variables. So why do we need to know about these symmetric polynomials? So first of all, our problem is symmetric, and that should lead you to try to think about these. And the most important fact about symmetric polynomial is the following. This is called the fundamental theorem of symmetric polynomials. It says that every symmetric polynomial is uniquely expressible as a polynomial of the elementary symmetric polynomials. So every symmetric polynomial like this one, we can have it uniquely represented as these elementary ones. Okay, so for example, for this one, if you just factor it, we get this, right? So you see, this would be a polynomial of STU, which I have just, this is my U, this is my SE. Okay, so this is a polynomial in the elementary symmetric polynomials, and we have unique, this is unique. Okay, you can the proof is not easy, of course. So if you get into university, you will see this is not really a very good mathematical statement. It leaves many things undefined. So for example, what is the field? What are the coefficients? But let's leave that out because we are at the high school level. Okay, the most important takeaway is that you can express, whenever you have a symmetric polynomial, you can express it somehow, okay, as using the elementary symmetric polynomials. So that's what we are going to do. Okay, so what's the plan? So whenever we try to solve a problem, okay, George Ployer, the famous author of the book How to Solve It, says you should have a plan, right? So what's the plan here? Well, the given conditions are symmetric polynomials. So given this fact, let's try to express these in terms of the elementary symmetric polynomials. Okay, and if the best scenario is that we can actually find out these values. Okay, so instead of finding out the values of x, y, z, we find out the values of STU. And you know, by this theorem again, we can express these in terms of STU. And if we know the values of STU, then we can find the value of these. Right? So that's our plan. You can try. You can, if you didn't know these facts before, you can try before continuing. So the rest is just algebra exercise. Okay, so let's first of all express this in terms of elementary symmetric polynomials. So let's say I'll just use the variables as above. So let's say my S is this, my T is this, and then my U is this. I already know that this is 1, right? It says S is 1. What about T? Well, where can we get T? You square SE. You square this. Okay, square this expression. So you square it, you get x squared plus y squared plus z squared plus 2xy 2yz. I just square both sides. And now by the given, this is 2, and then this is my 2t, right? and this is 1. Okay, so you can also find out t, in this case t is negative 0.5. Right. What about the last one? We want to find out what is u. So well, just by a similar so here you square, get this. If you cube it, okay, you will get so if you cube it, you have a lot more terms to deal with. Let's just preserve the XYZ order. Okay, so if you cube it and expand it, you get this. So I know that that is my 3 from the given condition, right? This is my u. What about these? This. So let's try to simplify a little. This is xy times x plus y. And you see, we can substitute this. So x plus y would be 1 minus z, right? So if you plug in 1 minus z here, 1 minus x, 1 minus y, it turns out we will get a t, this expression, and we will get minus 3u, and that is great because that tells us so substitute 1 minus z, 1 minus x, 1 minus y, you get xy plus yz plus xz minus xyz minus xyz minus xyz, so minus 3xyz. Okay, so that is t, which is negative 0.5. So we have 3 times negative 0.5. That would be, and then 3 negative 9 xyz plus 6. So, okay, so that is my u. So 0.5 is 3u, so u is 1/6. Okay, so we have expressed, actually when we express these in terms of these elementary symmetric polynomial, we have actually found out their values. So now we just need to express these in terms of these, and then we are done. Okay, but if you try to express these in terms of these using the similar method, okay, just cube and just bring to the 4th power, you will get, of course you'll get this, and then you get a lot more terms, and you will have a long time doing this simplification. Okay, you can do that. So one way is just following this route, just bring to the 4th power on both sides and then simplify. Bring to 4th or 5th power and simplify. That is one of the possible things you can do. Okay, but being an educational channel here, I try to show you some more tricks or some more technique. So let's go route 2. Route 2 is basically relying on something called Vietas Relation or Vietas formula or something like that. So basically this is talking about the roots of a polynomial. So this is about polynomial, coefficient of polynomials and its roots, about the coefficients of the polynomial and its roots. Okay, it's a relationship, it's some relations between. So again, let's have some Olympiad facts. So these are really not really Olympiad but advanced high school facts. So for example, if you have I think if you are in high school, you may have seen it before. So let's say you have a quadratic. Then Vieta says that the sum of roots, let's say alpha beta are the roots. Then Vieta says sum of roots is negative a, product is just b. So what if you have 3? And then you have alpha, beta, gamma are the roots. Then the sum. So basically the elementary symmetric polynomials. This would be negative a, okay, you see the negative just alternate. There would be an alternating negative 1 here. You see these are sorry, excuse. Okay, so these are called the Vietas relation. Okay, but you see these are just elementary symmetric polynomials. Okay, so if I know the values of these, that means I know the values of, or know the coefficients of the polynomials whose roots are my x, y, z. Okay, so that means Vieta gives us that if x, y, z are roots of this polynomial, then a equals x. Okay. So basically, in other words, you can just plug in these 1, -5, -0.5, 1/6 to here. Okay, but remember there is some negative. Okay, so I know that xyz is 1, this is -0.5, this is 1/6. So that means xyz are roots of the polynomial t3 minus t squared plus and minus 1/2 t minus 1/6. Okay. Okay. So once you know the values of the elementary symmetric polynomials, you can actually find out the polynomial whose roots are x, y, z. Okay. Why would we want to do that? Actually, I'm not planning to solve for this polynomial. Okay, we're just going to make use of it. So I told you, route 1, you can just bring this to 4th power, 5th power, and expand and simplify. Okay, you can do that. This is route 2, and because of my explanation, it looks long. But as I did it, when you know this fact, when you do it yourself, you don't have to do this, and then you just get, once you are here, and if you know Vieta, then you can jump to here. Okay. And why are we looking at this? Because we can do this trick. Let's put the cube power on one side and everything on the other side. Okay, because now to get t4, we just multiply both sides by t. But x, y, z are the roots of these. That means you can put t equals x, t equals y, t equals z, and it will be true. So if you put t equals xe, you have this. If you put t equals y, you have this. And if you put t equals z, so I think you can see where I'm going. If I just add these, that is what I want to find here, the sum of the 4th powers and the sum of the 3rd powers. This, I get the sum of the 3rd powers, which is 3. Okay, so that would give me that. And you can easily do x to the t to the 5, right? Right, so t to the 5 would be just t4, t3, t2. So if you just imagine, you plug in x, y, z, and you sum t to the 4, that means x4 plus y4 plus c4, you get this. Okay, and you will get, and you get 6. Okay, so it looks like my explanation, my solution is very long, but basically I'm trying to explain to you these facts here. So when I do it, I just need to do this part. and then I found out the values of the elementary symmetric polynomials. Then I just compose this polynomial. I can multiply t and just multiply. Well, I don't even have to write out these, right? Anyway, so that is the solution of this problem. Okay, so again, every time when you solve a problem, please try to reflect on what's the key steps. The key step is that if you realize this, okay, every symmetric polynomial is expressible uniquely as the elementary symmetric polynomials, then just make use of the elementary symmetric polynomials. Okay, so whenever your problem is symmetric, well, many competition problems are symmetric, and you can try to substitute using the elementary symmetric polynomials, and it will become simpler. Okay. Also, instead of route 1, which is just brute force, okay, bring to high power and simplify, you can make use of this Vietas relation, okay, because you see these are elementary symmetric polynomials, so quite often you can combine Vieta with elementary symmetric polynomials. Okay, you can make it a combo, okay, and then you can quickly solve many problems. Okay, so lastly, as usual, let's give this a difficulty score. This would be a typical National Olympiad level. So let's say 5 out of 9. Okay, and the character for this level would be Sasuke. Okay. Well, because he is like the strongest young ninja in Naruto. This is like, well, this is let's say you can maybe a grade 10, a very bright grade 10, grade 11 can do this. So that would be like Sasuke. Okay.